Hey everyone, I'm TJB Chris. Welcome back to the channel and welcome to the actual part 4 in my series Exploring 513, a look at the Memorex VIS. Tonight in part 4, I think we're going to be diving into the most practical video in the series, at least thus far, when we're going to be talking about developing software for the MS-DOS environment on the VIS. Particularly, we're going to look at some of the VIS hardware that's going to be most relevant to you in doing your initial writing of applications or porting of applications over to the VIS, specifically the hand control, and also the video. We're mainly going to focus on the MS-DOS compatible modes for the video. I'm not going to go into the VIS specific OEM modes tonight. I really want to go with a focus on getting a feel for the hardware and what you might want to look at if you're going to start to port things. We're going to revisit some of the differences in the platform from the PC that I've discussed in prior videos with a little bit more detail, and then we're going to take a look at porting an application over to the VIS after we do some basic exploration of the hand control in the video. So when it comes to the examples we're going to walk through tonight, I'm going to use a number of different languages from easy button on up to difficult. And the reason I'm going to do this is A, to show you that you might need to look at more than one language or more than one solution depending on what you're doing. But 2, to show you that there are multiple ways to interact with the VIS and to write software for it, and you don't have to start with the hardest, and the easiest might not be as flexible as you like. So you pick and choose. Now, this being a Microsoft platform, and particularly a 90s era Microsoft platform, you're going to have the best luck with Microsoft tools. It's the most integrated. But as you'll see, other vendors' tools can be used to work with the VIS depending on what functionality you're looking for. Now again, I won't be touching into modular Windows this evening. I may revisit it at some point. I know I said I wasn't going to, but there are Microsoft extensions that if I'm feeling adventurous, I might try and look at in a later video. Now you might be wondering to yourself, but TJB Chris, you showed all those unobtainium cards last week. When are we going to get to see those? Will we see any of those tonight? And the answer to that question is probably not. This video is already going to be long enough, and I wanted to get this one out of the way. The cards kind of came in between, but I do have a plan. My next video is actually going to be on the Save It cards. And as you saw in the last video, the Save It card has its own expansion card, and I think that's going to make it a lot easier and more fun to explore the Save It card, and we might even get to do something that probably hasn't been done since Tandy did it back in the 90s. So stay tuned for that video if you want to see the expansion cards, and then moving on beyond that, we'll probably do a video specifically related to those by themselves, because I think they deserve their own video, and we'll just kind of explore through those together. That one will be a little less put together and a little more exploratory. Let's get right to taking a look at developing applications for the VIS. And the first thing I'd like to do is walk you through some of the differences in the hardware that we've talked about already, and we're going to take a look at a couple of example applications that I've written in QuickBasic of all languages, and one with a little dash of assembly on the side, so that we can get an idea of how to interact with this wonderful hardware. And the first place I'd like to start is video. Now, as you can see up to my left, I've got the initial video modes for the VIS up on the screen here, and this is from VIS BIOS documentation that is on the Modular Windows SDK. Now, as I've mentioned in previous videos, though the Memorex VIS shares the video DAC from the Tandy Sensation, same DAC, it does not support all of the standard PC video modes. Particularly, there is no text mode. I know you might have seen one in the past. I mentioned it was a graphics mode, and tonight we're going to prove it. But also, it doesn't support CGA modes, most EGA modes, and EGA palette support is kind of static and limited. It doesn't support dynamic palette updates, for example. So as you can see in the document to my left, there are support for 2 EGA modes and 2 VGA modes. Everything else is OEM. Tonight we're going to look at the VGA and EGA modes only. We're not going to focus on the OEM modes. They're their own ball of wax. But this is important because a lot of applications use a lot of different video modes, and they may not work. And something you might actually find interesting is there are some modes that are not listed in the documentation that do seem to work. Now, how that's going to play out in real life if you actually write applications against it, I don't know, but you're still going to see that anyway. So let's start there. All right, I'm a little off center in the frame. Y'all just going to have to deal with it. All right, so I've got my development PC here. This is the Franken-Tandy 4833 LXT, as always. And as you can see, I've got my wonderful little menu system that I've made for me here. So our first couple of demonstrations are in QuickBasic 4.5. So as you can see here, I've got my MASM option here. I'm going to choose that, and that will give me QB45. If I said I should see that in my path, oh look, I do. QB45 right there on the end. Anyway, I've got a source directory, and I have a program called Screen. Now, Screen is a short, really stupid MS-DOS utility I wrote that essentially emulates the QuickBasic screen command, but with an added bonus. It will take screen and whatever mode number you provide it, set the video mode on the VIS, and then it will draw a triangle with a blue fill and a green border. That's the difference from the QuickBasic screen command. Now, a very important point, as I pop up a chart for you to show the various screen selection codes, the screen numbers used to pick resolutions in QuickBasic are not the same as the numbers used in int10H calls. So for example, the EGA mode 0D to call 320 by 200 by 16 is going to be screen 7 in the chart that you see in front of you. And there are others that vary. So 0E, of course, would be 640 by 200 by 16, but that is screen 8 if you're in QuickBasic. And so I just want to set that out there for you. The screen codes you're going to see here are not the numbers listed in the VIS BIOS doc. That's because QuickBasic has its own nomenclature for screen video mode assignment. Okay, so let's take a look at my utility here. I'm just going to run QB screen. And this should bring up my very simple and stupid source code. Now this does no checking for sanity checking for parameter inputs or anything like that. You just type whatever you want in the first parameter. It's going to give you whatever the numerical value of it is and pass it in as a video mode. So, but it's just me using it, so who cares? So let's go down and take a look here. Of course, like I said, just screen, val, whatever comes in the command line. And then we simply draw our triangle, and I've got it variabilized up there in case I wanted to mess with it. Starting position, sorry, move to the starting position, and then we draw it. This get it, we didn't actually do anything. You'll see that later. And then we just loop forever. Now, funny thing about the VIS, if you do something like an $a equal in key $, for those of you familiar with BASIC, to try and loop until, so for example, if I were to do $a equals in key, not kidney, and then while $a equals $, if I do that on the PC here and run this, that's going to work. Of course, assuming I take this out. But it will work. It will wait until you press a key. If I run that on the VIS, the program will draw the triangle and immediately exit because for whatever reason, probably because the keyboard is not completely AT compatible in there, it thinks it gets a key and the program immediately exits. So booting the VIS doesn't take very long, and for simple mode testing, I'm just going to Control-Alt-Del my way out of it rather than kind of try and deal with the keyboard in QuickBasic for a simple, quick, and dirty video program. So let's pull this back out. So let's walk through compiling this. I'm not going to save that because I changed it. We're going to BC screen. I want screen object. We're going to link screen, and that'll do screen obj. I want screen exe. QB 45, bcom 45.lib. I want a standalone executable. Okay, so now we have a compiled executable. Let's give this a run on the VIS. Now what I'm going to do here is I'm going to use the serial loader card. And this is one of the best things about the serial loader card is prior to this I would have to burn this to a CD and then take it over and put it in the VIS, and it would waste time and plastic. So now with the serial loader card, at least temporarily in my possession, I get to do this bit of fun. So you'll notice at the top of my menu, just under my little heading, I have an RF server start serial loader and TSR service. So I wrote a little bash file. And I'm going to point this to c:/wax source wax screen, enter. Okay. Let's flip over to the VIS and boot it up. Now over at the VIS, you can see I've got the Haiku file system and transport layer found screen up. MSCDX extensions are loaded. So I'm going to Control-Alt-Del this thing. I've got a keyboard connected. And now it should find the server over on the 4833. It just did. It's booting. And I should get the insert disk or cartridge prompt. So I'm just going to take this. This is my very base, not much on it CD-ROM. This is directly from the 513 archive, Frank Dirta IV's archive. And it has a CDG player on there, but that has a control.tat and browse.com, which I demonstrated last time. So I'm going to move the hand control out of my way, wait for this to boot. Now, if you remember from my previous video, when I set RF server up to a particular directory, what that does is the directory I point it to gets mapped to the root of the CD-ROM, and then any subsequent subdirectories become mounted as subdirectories of the CD-ROM. But as you recall, if I list a directory of the files on the server don't show up. They don't come up in a directory listing. Now, let's take a look at the program I just wrote just by running it, because if you remember from the last video, it's already there. So I'm going to run screen, and I'm going to run a mode that I know works. That's going to be screen 13. This is 320 by 200 by 256 colors. It'll take a little bit to load. It's going over the serial cable. and I should get a triangle. Well, there you go, folks. Now, believe it or not, this was my very first program for the VIS that I wrote. The mode selected and the basic commands worked. Fun fact, if you try to use the print command to print text on the screen, that doesn't seem to work. So just keep that in mind there. Now, to get out of this, as I mentioned, I've just got to do a loop at the end, so I'm going to Control-Alt-Del this, and let's walk through a few of the other video modes and see what might be supported. Now, as we mentioned, both screen 7 and 8 on the QuickBasic number assignments should be the 2 EGA mode, so if I go screen 7, I should get that. And this again, 320 by 200 by 16. And hey, look, it works. Now, this next one's going to be a little fun. Next one we're going to do is 640 by 200 by 16. That is the EGA mode, 640 mode, and that is mode 0E. And that is screen 8. And now if I run screen 8, there it is, friends. Proof that the text screen you're looking at isn't a text screen at all. It's a graphics mode. Because the mode was already selected, it didn't clear the screen, so it just drew the triangle over the text screen, which is actually the 640 by 200 video mode. So there you go. This is a graphics screen impersonating a text screen, friends. So just thought you'd like to see that little thing. In case you thought, TGB Chris is crazy. That's a text screen. I know a text screen when I see it. Well, apparently you don't. All right, we're going to do one more of these. I'm not going to go through every mode that it supports. But what I would like to show you is a couple of modes that are not officially supported but do seem to work. So let's take a look at 640 by 350 and 16 colors. So that is going to be screen 8, 9, 9. Okay, there it is. Looks a lot like 640 by 400, but of course it's only 50 pixels shorter. There's our triangle. Now that mode is not officially supported according to VIS BIOS. So if you do play with it, it may not work correctly if you go to do fancy stuff with it. But it at least seems to start, and we'll do screen 10, which is 640 by 350 by 2. And this is an interesting mode. I was surprised to see this in here. I was just kind of typing numbers into it. And look at that. And the border doesn't render quite right, but you can see the top and bottom of the triangle there. We've got a little orange to us. But let's do one more thing. I'm going to run a screen mode that I know does not work. Let's do screen 0, the text mode. And screen 0. And it should just explode and come back to me. There it goes, it cleared the screen. And if I do screen 1, we'll do a CGA mode. You're going to see that the screen's going to clear, but nothing's going to happen. And the triangle won't come up. So again, this is a pretty good demonstration that yes, it looks like a PC, it smells like a PC, it even utters some letters that PCs use. VGA, EGA, VESA. But not all of those modes are going to be supported. Stick to what's in VIS BIOS and you'll have the best luck. So that's a pretty simple program. That gives us a pretty good idea of the MS-DOS compatible video modes that we're used to and what we might expect to find. Well, okay, so we've got something on the screen. How the hell do we interact with it? I want to work with this, the hand control. Well, let's take a look at that. Now, the VIS hand control is accessed via int15h services. As you'll remember from a previous video, int15 is the ISR for custom VIS services, and that includes system status, the hand control, as I mentioned, wavetable, mixer, synth services, timer, keyboard. There's a bunch of custom VIS services that are available in int15. Now, the VIS hand control itself has two different methods for which you can kind of check out what its status is. The first, of course, is you can poll it. Just keep asking it, what's your status? What's your status? You know, is A pushed? Is A pushed? Is A pushed? And what VIS will do is give you back a 16-bit value with the binary status of each button on the hand control, of which there are only 10. So there are going to be 6 bits unused. And these are reserved, probably for future use, VIS2, some other modular Windows platform, what have you. The other option is you can tell VIS, I've got a program, you know, here, and anytime someone pushes one of these button thingies, go here, run this program, and then get back and go on with whatever you were doing. So for our first example tonight, I'm going to go for the former. We're going to look at polling, and we're just going to ask the controller what its status is, and then we're going to react based on that. Later in the video, when I talk about porting applications, you'll get to see an example of setting up a routine that VIS can call on its own every time a button is pressed or released. So what I've got here is I've got, again, in my Microsoft Macro Assembler and QuickBasic environment, I have a program called VIS Control, and it has two different component parts. There's an assembly language component, which we'll look at first, and that component does the actual BIOS calls to the hand control, and then the result gets passed back to QuickBasic, and this gets assembled as a QuickBasic library. Now, fun fact, I'm not going to get into writing these and assembling them as QuickBasic libraries and then interfacing with them in QuickBasic. That's detail that you can find on the internet, so it's just too deep a scope for this video, but it can be done. I figured it out in a short amount of time. If I can do it, you can do it, folks. Now, taking a closer look at this routine, I'll walk you through it. The first two steps here, the hand control returns its status in two registers. Hand control 1, whether you're solo or the switch is in player 1, is going to come back in the CX register. Hand control 2 will come back in DX. They both come back at the same time, and as I mentioned, each register is a 16-bit register and will contain the state of every button on the controller every time you call it. Now, when you call an int15 service, you call it with int15 AH always equal to 71 hex, and AL will be 1 in this case for hand controller services. AL will be different if you're calling different services. Now, within the hand controller services, AL1, there is a sub-function code, and that is BH. In this case, BH1 will read the hand controller state, 2 and 3 will get and set the switch handler, and we'll talk about that later. So, this is pretty simple. QuickBasic takes its return values from the AX register. So all I have to do is call int15h with BH1, AH71, AL equals 1, and then the value that comes back, which is already in CX, move it over to AX, and then all I have to do is pop DX and CX back so that they're wherever they were, so that QuickBasic is happy when it resumes execution, and we're right back where we started, no problem, and we return. From an assembly standpoint, it's that simple. All I have to do is get the value from CX into AX where QuickBasic expects it, and then I can go look at it in QuickBasic. So let's do that. So let's go QB VIS CTRL.base. And now, another thing I wrote in June. I was very busy on June 18th of this year, my friends. I had a good time writing all this stuff. And now, of course, if you're running this, of course, on a machine with a development card, you need to do /L, but we're not going to do that. You just compile it with BC again. And except when you run the linker, you have to link the assembly library in. Anyway, here's what we do. You're going to recognize some of this. So we've got our triangle here. Hey, look, our starting position, A61, B equals 1. We set a VIS compatible screen mode. That's screen 13, 320 by 200 by 256 colors. Set the starting point for the triangle. Draw the triangle. You recognize that. Now the get is going to be important. So here's what we do. I want to move the triangle when you push a button on the hand control player 1. So if you push the buttons on the D-pad here, I'll come closer, push left, right, up, down, I want to move the triangle on the screen. So what we do is A equals get hand state. You'll remember from the previous program in Programmer's Workbench that get hand state was the name of the proc that I had written in assembly language to get the status of the controller and move it to the AX register. That's the return value that gets stuck into A. And then what I do is I look at the bits. If A and 1, then upgrade up the y-axis, y plus 1. If it's 128, subtract x, 1 from x. If it's 256, subtract 1 from y, and it's 512, add 1 to x. And then what we do is we put the triangle and go back to the loop and keep asking. So literally, this loop just keeps asking, 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 asking. And if any of the bits are set that it cares about, 1, 128, 256, or 512, then it will do the corresponding action. So pretty simple, right? Let's take a look at it in action. So the first thing I have to do, if you remember from the screen demo, is I had set RF server to the source directory that had my screen utility in it. And that put it in the root of the CD-ROM. Well, you can't really uninstall RF server, so I've rebooted the computer. We're back at the menu without RF server, so I'm going to reset it up, this time pointed to my VIS control directory. Source VIS CTRL. There we go. Now, let's flip over to the VIS. Now over at the VIS, let's give it a 3-finger salute here, and it should rescan the files. As you remember from the previous video, you've got to reboot the VIS if the files change. And now we're booted up. So we should have a, of course the file's not going to appear here in the directory, as you know. We should have a vis ctrl executable. I can hear the hard drive loading, and I should get a triangle. And I get a triangle. All right, here is my controller, and I can move it up, down, all around. Now, as you can see, when I was dealing with the graphics straw, I didn't quite plot the black border around it enough to erase it, but as I move left, the thing goes left, right, down, up, and it works. And I have a little bit of boundary checking in there so that, of course, if I go off the edge of the screen, because if you go off the edge of the screen, the program will crash. I found that out the hard way the first time. But that's basically how it works. So what you're seeing here, this is the very first thing I ever did to make the VIS hand control do something myself. And I felt super accomplished for something that's rather trivial, but it was kind of fun. And I guess as the first person to have done that in a while, I guess it is kind of fun. But either way, not perfect, but it at least gave me an idea. I didn't bother dealing with the buttons. The bitwise parts are easy. Once you get this part, it's all pretty simple. And that's the basics of the hand control, at least polling it. So with that in mind, let's talk about getting applications onto this thing that aren't just stupid hand control and screen demos. So before I get to my first example, I want to run you through some exercises I tried when I first got the keys to the kingdom, when I first got MakeTat and the ability to make my own control.tat files. And that is, I took technically compatible PC applications that ran on a 286, supported EGA or VGA graphics. I burned them to a CD just to see if they would run on the VIS. Now, I knew full well they weren't going to work, or parts that they might start, but you might not be able to interact with them, or other things might happen with that. Just knowing that the VIS wasn't entirely compatible was just different enough. But I wanted to see which applications would start, how far they would get, and if any would do neat things like interact with the keyboard or let anything else go. Obviously, the hand control wasn't going to work because that's its own custom little beast. But remember, the audio is ad-lib. The video, if you use the right modes, is EGA or VGA. So if you don't have any input, you still might have a pretty good idea of what kind of applications might run on the VIS. So let's walk through a couple of examples. And back over at the VIS, the very first thing I did was I found a copy of, I guess, one of the more popular games for the IBM PC, Prince of Persia, which got its own disk. This has its own control.tat file, and I literally just took the disk, or the distribution for Prince of Persia, wrote it to the root of the disk and told control.tat, hey, run prince.exe. And this is the result. Now this is before I was making Class A titles, so it's not going to say it's authorized, but it is in fact loading. That's a graphics screen saying loading. And as you can kind of hear, I have the volume down for the VIS. The audio is working. The game starts, and the demo sequence begins to run. In fact, the entire sequence runs, and it'll run over and over and over again. Now, one interesting thing about Prince of Persia, like so many other DOS games we're going to see, is that as the VIS BIOS documentation notes, applications that hijack int9, it doesn't use the word hijack, but I do, that hook int9 hex, those applications will not work correctly because the VIS's keyboard is not entirely AT compatible. And so what will happen here, you're not necessarily going to see it, but if I push the unblock keys, the lights go on and off, but not with the keys. It'll flash or flicker. None of the keys do anything. I can't start the game. It literally, the hook into int9 breaks it, and it won't actually do anything. And of course, this version of Prince of Persia is keyboard controlled, so there's just nothing you can do with it. But aside from the keyboard not working, the game looks functional. The animation is good. It's fairly fluid for VIS, just like it would be on the PC. It's colorful. The audio works. We have ad-lib audio. So this would be a game that if we had the source code for the DOS version, we could probably make this work. Now, as far as I know, the original DOS source is not a thing. There is a port that allows you to compile modern versions on modern platforms, Mac, Linux, DOS, and that is pretty heavily modified from what I understand. But I don't think I can just compile that for a 286. That's not going to work. And then, of course, the 6502 version is available in source, but I'm not porting that over to x86 to then port it. I don't have those chops, folks. So if this game ever showed up, it would be a good candidate, but because we don't have direct source for it, at least none that I trust to not get stuck down like 17 waterfalls with, this isn't an option. And here you can watch the demo run out. It actually does play. He jumps, spikes come up. It's pretty responsive. It's really kind of sad that I don't have a way to port this over. We don't have the source code. Now maybe someone in the comments will tell me, but there is real source code. Again, not that, I think it's an SDL pop or whatever it is. There's a GitHub repo for the modern ones that you can compile on Linux, Mac OS, and Windows, and that's not it, folks. And again, the 6502 port is not an IBM PC, so no. But, I mean, it really is pretty responsive, and I think if we could get this, it would work well. So this is one of the first applications I ran. Would you like to see another? Well, I don't care, because you're gonna. Of course, we're going to eject the disk, and it did not reboot this time, but that's okay. And we're going to hit Control-Alt-Del. And so one of the other games I tried, what I did was I have a Grand Old Games account, and so I downloaded a bunch of games. And so let's do MM3. This is Might and Magic 3. And I'm going to show you the different litany of issues and errors that you'll get. And this one actually uses calls that are compatible with the VIS's video display to tell you that there are 0 bytes free on your hard drive. That's because there isn't one. It needs at least 100K for temporary files. So please free up some space. That's a bust. The other one I tried was Ultima VI. Now, Ultima VI is interesting in that, like Prince of Persia, it starts, but it's not quite as successful. And you might hear the drive seeking in the background there. Like Prince of Persia, still seeking. This can't be easy on this poor old drive. Seek, seek, seek. There we go. Like Prince of Persia, there's music. Screens are pretty fluid, solid. You even get the animation. This is where we end. Now, I haven't played this game on the PC. I suspect that maybe there's some input here that's needed, but again, with a keyboard, this thing probably hooks int 9, or it has other controls. So I haven't played the game enough to know. Maybe if it supported like mouse or something, I guess you could do something, but it's not responsive, and it never gets past the screen. You can let it sit here forever. It'll play the music. It'll keep doing this loop over and over again. But this is a game that kind of pretends to do something. Not bad, right? So I did this with a few other titles and kind of got an idea of what type of applications, what era of applications would run on the VIS. I also tried some CGA and EGA applications, not having written my own screen utilities yet. I tried the horrid, was it Mega Man 2 or 3 that was for the PC. Fortunately, that didn't run. But that was kind of a neat way to kind of get an idea of what would at least try and start what the VIS was capable of. Was it standard enough and ad-lib support and other things that some applications that could find the hardware would run with it? The answer to that question is yes. The graphics mode, same thing. If it's one of the 4 compatible modes, it seems to be pretty compatible and it seems to work. Our first project that we're going to look at tonight in terms of actual porting software is the TRS-80 Color Computer 2 emulator by Jeff Vavasour. I hope I pronounced that correctly. The Coco is my first Tandy platform and my favorite Tandy platform, and the one that kind of was the seed for all the rest of this stuff that I do now and what's been a, so far, successful career. But I figured this was an easy one, and it actually was a fitting one because it harkens itself to the VIS well. It technically runs on a 286 processor. It supports VGA video modes. So it looked like it would be a good place to start, even if some of the VIS eccentricities might get in the way. So let's take a look at the Coco 2 emulator here on my 4833. I'll just give you an idea of what it looks like for those who haven't seen it. And it's pretty straightforward. This went all the way up into 2001. And if I just hit escape here, I'm going to get an extended color basic prompt. And of course, I can list and can print. Hello, you, Rummy Buzzard. Not a Coco phrase, but you know. Apparently, again, camera, can't type. There we go. And this thing does map the keyboard, just like a PC keyboard, although I think that's an option. F6 brings up all the options and things that I can do to look around here. Like keyboard mode PC, there's Coco, custom Dragon. There's a whole bunch. There's mouse support with the joysticks, clock frequencies. You can do DiskBasic if you put the disk ROM on here. And of course, I can exit to DOS with Q to quit. And yes, I can quit. So that's what the Coco 2 emulator looks like on the PC. So here's what we're going to do. We're going to set the RF server for the serial card over to this Coco 2 directory, reboot the VIS, and I'm going to show you what happens if you run the untouched emulator on the VIS. So let's do this. Server C:\\Coco2. All right, and let's head over to the VIS. Okay, over at the VIS, we're just going to three-finger salute this thing. And look, it got some files. The RF server's running. And I don't have a disk in there because I forgot I took it out. So let's put that back in. And there's browse. And of course, like usual, files aren't there, but we should have the Coco file. So Coco. And it's going to take a little time over serial. Now this is an interesting error message. So this says here, error loading, and just a bunch of blanks, .rom, no carriage return there, and I get my A prompt back. That's kind of curious. The ROM is clearly there. We know it's there because it ran over on the PC from the same directory. But of course, the blanks kind of give us a clue. So let's go back to the PC and see what happens if we were to rename or remove the ROM to see what the error message should look like. Okay, back at the PC, and we'll just do this. What I got for a ROM file here, ren coco.rom, coco.rrm, and let's run Coco. It says no files found in the path, and it turned off my cursor. Great. So that's one of the couple of possible error messages. The one you saw there would normally say coco.rom, possibly, but you get one of a couple of error messages. Now, you'll notice that for color computer folks in countries that aren't America, they use the U, or as you would call it, the proper spelling. So I thought that was kind of interesting. Now, actually, if I ran that back, did he call it color in the emulator itself? Well, let's find out. Sorry, a little tangent here. Oops, room, coco.room. He does couleur, the TRCD couleur computer. Okay, just curiosity. Yes, I'd like to exit. And now, of course, my cursor's gone. Okay. So what is it about the Color Computer 2 emulator that causes a problem? How can we find out what might be going on? Well, it turns out that there is a utility called DOSMON that we can use to see what's happening with underlying DOSINT21 calls when you run an application. And the way this works is that you invoke the application, you can set up a terminal, such as the DT100 here to my right, which will now power up because we're going to need it. And there it goes. And now I have to actually disconnect the VIS from COM1 because DOSMON also uses COM1, and it is not necessarily able to be easily changed. So I did try patching it around like I did with the ROM, and I had less success. So didn't really spend more than about 20 minutes on it. I kind of gave up and thought, you know what, I'm just going to swap the serial cables, which is what I'm going to do right now. Now with the DT100 in frame, I had to reboot the computer because, as you recall, RF server was running already on COM1, and so I can't run DOSMON on COM1 as well. It will cause a problem with the other two TSRs, so I've rebooted. And again, now DOSMON at least has the ability to remove it from memory, but RF server does not. So let's go to VIS, Tandy, MS VIS, which is where it was in my archive. And we have DOSMON.com. So if I actually do DOSMON/question, you can see I have /d to deinstall, and it runs on COM1, and it monitors int21h activity. It sends error messages when an attempt is made to call an int21 function that is not supported under HaikuDOS. Now, the interesting thing is, as you'll see, it does a little more than that. So let's give it a run. And now DOSMON is installed, and you can see on the terminal here that we have some invalid DOS functions already, because as I'm running command.com, as I'm typing, it already sees things that it doesn't like. In fact, let me switch you over to just the G70 here, and I'll give you a better idea of what the screen looks like. And here we are. You can see here if I run a file, so if I type edit here, it's going to see edit.com, which calls QBasic.exe, which runs a bunch of invalid DOS functions, 44 and 33. So in addition to listing the files that, or the calls, I'm sorry, that are invalid. It gives you a good idea of what files are loading and the like when you run an application, how far you're getting into your application, if it's crashing, stuff like that. So it's pretty cool. And again, this runs on the PC side only. So with this in mind, let's go run the Cocoa emulator. Now, keep in mind that with this hooking int 21, it is going to slow down the machine dramatically. So we're not expecting speed here. We're really just interested in the calls. Okay, ignore those. Here we go. Okay, here comes cocoa.exe. And taking a closer look at these functions, function 11, and these codes are all in hex, in case you couldn't see that. Function 11 is find first file. So the Cocoa emulator looks like it's going out trying to find the ROM file, which would make sense. ROM files could have different names, there could be more than one. So find the first file that's a .rom file, and we'll see exactly what it's doing in a minute here. And then it goes to find any subsequent files with function 12. So find first file is 11, find next file is 12. And 44, if I go looking it up here, because I didn't, I forget what it was. And 44 is a device driver control. And this passes information directly between an application and a device driver. Not exactly sure what that's doing. As you'll see later, that's not something we necessarily have to address. It'll fail silently on the VIS, so we're going to leave that one alone. So now let's go back over to the 4833 and see if we can take a look at the Cocoa 2 emulator source code and get an idea of what exactly is happening. All right, so let's unload DOSMON, first thing we want to do, because I'll give you an idea here. If I don't unload DOSMON, this is what's going to happen. Is it's writing all those invalid function calls out to the terminal. It's slowing down DOS quite a bit. So let's just go. And there we go. DOSMON is now removed from memory. And now I'm good. So let's go into my source directory for the Color Computer emulator. All right, now in my source directory for the Cocoa here, I've got two versions of the source on here. I've got my modified one and I've got my unmodified one. And if you remember the first function call from DOSMON, we're looking for any int calls for int 11h. So we want to go look there. So the first thing I'm going to do is I have my backup unmodified source right here. Let's go to MASM. And what I'm going to do is I'm just going to use the MS-DOS editor actually. And I think it's in cocoa.asm. Okay, this is perfect. So what I want to do is, in order to find this, I want to see if I can find the phrase error loading and kind of work back from there. So there we go. Okay. So this gives us actually a couple of good clues. So the first thing here, message 15, is error loading, and we have ROM name, which is all question marks ROM. So that might help explain why we got the error loading blank 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 dot ROM. There are 8 blanks, I wasn't going to say that 8 times, on the VIS when we went to go run it. So clearly when that find function failed, the find first file function failed, say that 5 times fast, find file function failed. I digress. We clearly had some sort of issue where this didn't get populated. So let's actually search for that now. Find ROM name. And here we are. Okay, we've got some bits here. Okay, oh, start 1 has an int 11h call. Move AH into 11, int 21h. Okay, so this is our call. We found it actually pretty simply. And believe it or not, when I first went through this is exactly how I found it. I got stupid lucky, and it was really easy to find. So we found our int 11 call. And what we're doing here is we call int 11, go to the offset of ROM search, which, if you remember from the top, I don't remember where that was. I don't want to buy it. There we go. Was right around the same area here. It was defined up here as question, 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 question ROM. So this is the search string that gets passed down to the int21 function call for function code 11 to tell it what to do. Let's go back to F3 that, and it's going to take us right back to start 1. So here we search for the ROMs, and if we find one, we jump down to start 2 here, JNZ, to jump 2, and we get the ROM name. Let me go back. Off message 14 if we don't find anything. And what's message 14? MSG14. And of course, there we go. No color computer files found in the default path. And of course, we have our error loading message that we saw before. Search, find, error loading that we used just before. So there we go. Message 15 was error loading. They're not in order. That makes it fun. Back to our code. Back to the lecture at hand. Tell me what song that's from, friends. So without walking through the entire bit of code, in short, what's happening here is it starts the ROM search here at start 1. If it finds something, it goes and tries to get the ROM name, and then moves on to start 2A, tries to load the thing. And if it doesn't, then eventually in here I'm going to find message 15 right there. If we get an error message 15. And this is different from the PC call that we got, or the PC error that we saw, for a very good reason. And that's because if the emulator thinks there are no ROMs available, it'll tell you. But if it thinks there's a ROM available, and this is a clue, then it will try to load that. And because the int21 call for function code 11 failed, it didn't find the first file, and it didn't update the name ROM name, but the call appears to have passed because it tried to load it. And this comes down to how unimplemented functions return. Sometimes, as is the case with these functions, when the function fails, it returns with a code in AL or another register that causes the program to think that it was successful. And so when it thinks it's successful, it moves on. And of course, that comes down to must have come back with a non-zero value, which it probably did. So even if it was -1, that still would pass the non-zero test because it's not 0. So of course, that drops us down to actually trying to load. And of course, if it's trying to load question, 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 blah, 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 .rom, it's not going to work, and it's going to error out. So what do we do with this? Well, since those functions are unimplemented, I can't have it go dynamically searching for ROMs, and I already know the name of the ROM. So what I can do is take out my hatchet and bludgeon this code such that it's just stupid and tries to load a hard-coded name. And that's exactly what I did. So let's take a look at what I did. So let's open coco.asm. And now, I'm going to search for start1. Search find. Instead of searching for the messages, I'm going to search for start1. And here we go. And you can see here, we have simplified the code quite substantially. Start2, start2a are gone. And then the error message is here if it can't load the ROM. And we simply move the offset to ROM name. We make the int21 call to load the thing. And we move on. Start4 will go and do whatever else needs to be done. And you can see if we jump down to start4, otherwise the error pops up. That's all it does. It's fairly simple. And to fix the ROM name problem, I glossed over that. I literally changed it from question marks to coco.rom. And that's it. So now, instead of trying to find the files, I have forced it to load coco.rom and taken out all of the search functionality. Now, for a dedicated application like this, on a player like this, it may not matter. You control the disk, right? This is a CD-ROM-based platform. People aren't going to be dynamically adding files in the default configuration, and you could probably add an additional update to do a secondary load of the disk basic ROM if you wanted to do that. But as you'll see, that's not really, there's no point in doing that. So that was really all I did to make this work, is go and take out the file calls. Now again, I mentioned the function code 44. I've run into a number of applications that try and do the device control. I haven't dug into exactly what they're pushing, what devices they're talking to, probably a disk. But because it seems to fail silently and these applications continue to run, and I'm not worried about doing file I/O, if I can get the thing to run and just load the files it needs to function, I'm going to ignore the int44 calls. It does assemble, it does run. In fact, let's take a look and see what happens if I run Coco on the VIS. So what we're going to do here is we're going to run the RF server, and we're going to point it to the VIS compiled version of the Color Computer 2 emulator. And now we're going to move over to the VIS, and we're going to give it a start. And back at the VIS, oh shoot, I've got to plug the VIS back in first to the PC because I have the DT100 plugged in for DOSMON. All right, all plugged in. Let's give her the 3-finger salute. And we are connected because the VIS is booting. I can't get comfortable in my chair. Downsides of standing up. Okay, and as usual, there will be no Coco emulator listed in the directory, but if I give it a run anyway, it should start. I hear the hard drive over there going. And it's going to take some time because this is, of course, going over serial cable. Even at 115 kbaud, it will take a little time. And there we go. Now, first things you'll notice, and this comes down to some of the video eccentricities on the VIS, I get the Coco's border. So I see the green border, but none of the characters render. And this is a thing you're going to run into with the VIS, again, given its limited implementation of the video. But it turns out I know the keys anyway, so I hit escape. It's going to sit here and appear to do nothing. But you can see the familiar nuclear green color computer screen, which is kind of cool. Makes me wish this worked a little better. And it's running very, very slowly. This is probably the slowest color computer ever. In fact, I didn't go any further than this. Once I got to this point, the keyboard works to bring up the menus and stuff, like I can hit F6 and the like and bring up the menus. But, and this is probably a function of just how absolutely slow this is going, typing doesn't do anything. I don't think I can get it to do really anything. But as you can tell, the keyboard is working. It's not hijacking int9, so the emulator does respond to the keyboard. Now, there may be some additional keyboard routines in there that are not VIS compatible, but again, once you get to this point and the thing's not really working at all or well, there's not really any point. So it's going to take a faster processor than this to run this on the VIS. And maybe you could tighten it up, maybe not. It's already an assembler, so yeah. But it was a neat exercise because this was a very easy one to try and start with something, get it working, and see if a compatible PC application would work. And I thought it was kind of fun to see the end of the Tandy line, the VIS, running something from very early in the Tandy line, that being a color computer. So there's our Cocoa content for the day. It's been quite a while since I've done anything Cocoa related, so it was fun to incorporate this. So that's the Color Computer 2 emulator, and of course, again, the menu doesn't show any of the text, but I know what the keys are, so Q to quit. You can see there's that dialog that on the PC looked all nice, and I can hit Y to quit, and it drops me back to my browse.com shell. So that was my first attempt to get anything to work, and I chose this specifically because I had the source code, it was available, and I was kind of looking to poke around with assembly a little bit and learn a little bit more about 8086 assembly. So now let's get on to something a little more useful, because, well, this was a fun project, and if it had been a little faster, maybe it would have been something to follow up with. I wanted to get something that was actually useful and playable on the VIS, and I wanted to use something that wasn't keyboard dependent. I wanted to use the hand control. So I went looking around for applications that I could try and run on the VIS that would lend themselves to this kind of control, you know, your video game style, Super NES style controller. And I found out that the source code to Commander Keen and Keen Dreams had been made available. And when I got looking at the game, it looked like the perfect contender. It supports EGA graphics, and it has ad-lib sound support, and it's a pretty standard, runs on lower end standard PC hardware. Let's take a look at Commander Keen on the PC. We're going to look for any immediate gotchas. We'll play through the game a little bit, get an idea of what it looks like, how it's controlled, and then we'll jump into DOSMON, see what that has to say, see if there's any other gotchas that we need to take a look at, and then I'll walk you through the source code a little bit, particularly what I did to change it to make it run on the VIS. So let's take a look. Back at the PC, ready to take a look at Commander Keen, and it is not only a new scene, it is a new day. I have a different shirt on, which means, of course, that time has passed. And yes, a fair amount has. It's been a few days. Things got a little busy, friends, but that's not going to stop us from finishing this out. So I've got the DT100 fired up, and what we're going to do is fire over to the DT100 for the camera view here. And then I'm going to run Commander Keen, and we're going to see what it looks like, get an idea of what's on the PC screen, and hopefully figure out what some of the gotchas might be for the VIS so that we know where to start looking in the source code. And the first thing we have to do is run DOSMON, so let's go do that real quick. And of course we can see on the DT100 we have output. I'm going to try and stay out of frame here. Just realized I might end up in the frame. Now that we've got that going, let's run over to the Commander Keen directory. And I have just a basic unmodified version of Commander Keen. And I can run KDreams. And it should start up. And of course right now we have our first little gotcha. The text screen. Mode 3 is not supported. 80 by 25 text is not supported. And this thing does look like it makes use of the text screen. Whether or not it sets it, I'll let you see that in the code. But it does make use of the text screen. And looking over at the DT100, we have a number of invalid functions. 44s are fairly okay. They tend not to get in the way, as I mentioned previously. But that 2C could be an issue. What is 2C? And of course, get2C is actually get system time. And as we remember from our previous discussions on VIS, the VIS doesn't have a real-time clock. It does not know what time it is, and it doesn't even keep a clock starting at 0 that just doesn't have a battery in it. There's literally no real-time clock. There's no real-time clock interrupts. We can see it loaded a bunch of files, the config file, a map file, the EGA graphics file, it looks like an audio file, and the save games for the various save slots on Commander Keen. All right, let's press a key. And of course we get the title screen. Looks like a nice title screen, EGA title screen. So you know the game runs, so you know it's going to be a VIS supported mode. And without pressing any keys, it's going to flip back and forth here between the title screen and the high scores. So I'm just going to push the space bar. And of course, it loads very quickly. This is a 486 DX4100, so it's going to go fairly quickly. And the menus, we've got our menus here. Now, the sound device is PC speaker. There's no sound card in this. On the VIS, that will be AdLib. And of course, it says turn music on or off, but one very important thing must be kept in mind, and that is there is no music. Future games using this interface will include music. If you have an AdLib or Sound Blaster, you can choose to have background music. Otherwise, no music. We try to make everything fit for Keen Dreams, but we had to opt for more levels and less frills, like music. We tried, believe me. Okay. Ask me how I know about this, because I started to wonder why the heck I wasn't getting any music, and then I R'd the effing M and realized that, oh, music's just not supported, even though the engine is in fact there. Okay. So you can see it's mostly keyboard driven. Actually, let's take a look at the help for the keys. We've got control panel. Actually, it's one up there, help with the controls. So moving key around. Control will take them in. Jump is control. Climb a pole is up. Throw is alt. So control, alt, arrow keys, duck is down, and there's some function keys that we can use. But otherwise, not too much. Okay, so let's see what the game looks like. We'll start in easy mode, and we go right into our bit here, and of course I'm on PC speaker. Does sound better with AdLib. Ooh, oh, pick that back up. There we go. And it's a nice little side scroll. Actually, this looks like something that should perform fairly well. I don't know what the minimum requirements are for this game. I'm going to pop them up on your screen for you now. But suffice to say, it looks like it'll very easily run on a 286, just looking at it. And that's kind of the impression I got when I first played it. I'm pretty sure this was for a 286. You can throw up. Just hold Alt and up. So honestly, with the limited number of controls and me sucking at this game, especially since I'm trying to play and talk, and also, yeah, I'll show you, candy bars. There's not a lot to the game. It looks like it would be fitting for the VIS controller. The main controls are fairly straightforward. So really, and as we look at the DT100 while I'm playing, nothing really came up. I got one more of the function code 44 hexes, which of course is a device, and it's device IOCTL, or some sort of device direct control. Not a big deal. It doesn't seem to stop anything in any of the work I've done on the VIS, so we're just going to leave it. But really looking at this, the game doesn't present itself as having too many problems for the VIS. The main issues we're going to have are that time and date, and we're going to have a problem with the text screen. So with that in mind, let's go take a look at some of the source code for the unmodified Commander Keen and Keen Dream source. All right, so I'm going to go here to, and then I should have a Keen master directory in there. Oh, let me turn off DOSMON. I almost forgot. Got to turn off DOSMON. As you can see, it's fairly slow with DOSMON on. DOSMON/D. There we go. No more DOSMON. All right, now, much better. And I'm just going to use the MS-DOS editor. Now, one thing I'll point out, this is written in Borland, Borland C++. Actually, it's Borland C. I use Turbo C++ 3.0 to compile it. That seems to work. So here I've got all of my C files. Let's actually look at what's there. They're interestingly named. We've got Keen Demo, KD Keen, KD Main, KD Play, and then we have a bunch of ID files with some various suffixes, two-letter suffixes in them. And so what we'll do here is we're going to start with KD Main, take a look in there. Okay, great. So the first thing we want to do is try and get our bearing. I'm going to show you kind of where I ended up going and talk you through what I ended up doing to try and find my way around this, because the game actually, with KD Main, actually really did kind of help me branch out and find my way around the game without too much trouble. So of course, the first thing I did, having that 2C, that date code being the first thing that I saw, I decided while I was in here I would search, find, and I would find date. So if I do that, okay, the first thing I see is an update text screen. And that says to me that obviously my text screen code is around here. So let's scroll up and see what got us here. And we are in init game. So, and this is literally where I landed the first time, folks. This is literally init game. So we have a few things we're going to want to look at here. We've got startup for the multimedia startup. We might have to come back to that, but maybe not. We've got some graphics mode checks, and we've got some errors if there's not enough memory to play the game, which of course probably won't display on the VIS because there's no real text screen. And then we have this guy here, US text screen. Obviously, we're going to want to check that out. And then we have a bunch of other, you'll see these 2-letter codes at the beginning here, and these line up with the file names, some of the file name codes that we saw at the beginning. You saw IDUS, IDIN, etc. So the second letters of those files are these guys here. So US text screen should be in IDUS, and it is. So again, IDCA, RF, SDUS. So all of those will line up with the various files. Since we're starting to figure that out and figure out how they did this, at first I'm looking at these file names going, what the hell were they doing? But then it started to make sense. So let's look in edit ID us.c. And I'm just going to look here for US text, I think it was. There we go. Okay. US screen draw called only by US text screen. Okay. Well, what's in here? Not much. Oh, but US text screen is next. And look at that. So this right here is something we can't have, obviously. We talked about this before. AL equals 3, called int 10, that's mode 3. That's the 80 by 25 text screen. That's just not going to fly. So the nice thing about this is they've got it all nice and packaged up. We've got text screen here. We get do our various setting up, US text screen, clear text screen, all this stuff that hopefully I can bypass simply by commenting out the US text screen. Prints the startup text screen. These are the only user manager functions that can be safely called before the user manager has been started up. So we're definitely going to want to comment that out. So let's go back into kemain.c. There's our text screen. Okay, so now we have VW startup, RF, IN, SD, and US. So we'll go through the next one of these that I had to go look through. So with the text screen found, I had to decide if I wanted to go on and follow up with that 2C get system time function call, that DOS interrupt call. And I figured, you know what, a lot of VIS system calls, if they're not implemented, often fail in a way that allows the program to proceed. And I guess in a way that kind of makes sense, right? If you're porting a DOS application, you've got something that isn't critical. See if you can fail in a way that causes the application to proceed, and whatever state it gets back, hopefully it can deal with. In the case of the system time, it's in a randomization portion of the game, which sets up the random number generator. And I did find that. Let's go take a look. And to find it, actually, Borland actually has in its tools of the era, 80s, 90s, Borland C++, Turbo Pascal, etc., has a grep utility. And since I used Borland C++ 3.1 to compile this, I used its grep utility. And if I run grep here, you can see I've got a bunch of options. It's got a fair amount of functionality. It's not as comprehensive as any grep that we're used to now, and it's not even probably as comprehensive as grep on my Model 16 over here and in Xenix days. But it does the job, and it supports things like case insensitivity. So if I look through the files here, you know, I've got my C files, my header files. I've also got some equates, and along with them, the matching assembler files. This game is a mix of assembly in C and also a lot of inline assembler in the C, as you'll probably see. And so what I thought I would do is just see if I could grep for 2ch the call and get lucky and find it either an inline assembler, I'll do it with -i, or if I could find it in a C file. So we'll just do star.star. And lo and behold, I have a 2ch there. Let's see what it is. And there it is. Get the system time. And it's in this time it function, so if I go search for that, it's up in the randomizing function. So this is a randomizer. Do I randomize? So I can either ignore it, or if it doesn't work, I can try and come back and deal with it, but I at least know where it is. And I got lucky on that grep with the 2ch. If that hadn't worked, I would have had to try like system, which wouldn't have worked, or time, which wouldn't have worked, or I would have get system time. Or I would have taken it to a machine with a more powerful grep and tried there. But either way, it doesn't look like something critical that I had to handle, so I thought, well, I'll leave it alone. And instead, I wanted to move on to the video modes, because while the video mode looked EGA, and we did see EGA elsewhere in the code, I wanted to make sure that it was going to be a mode the VIS would support, because there aren't very many. So to find it, I'm going to go take a look at my old friend Borland's grep, and we're going to see if we can find some easy button phrases, words, whatever, symbols that might give me an idea. So we're going to exit here. And again, we have our old friend grep. I'm going to see if I can find EGA anyplace. I'm going to look in my C files first, and of course there's quite a bit, so let's go through and more of that. And we can already see we have some, looks like compiler directives, gr mode, ega gr, there's a bunch of those. Pound if, okay, so there's a compiler directive, so that's a good clue. So let's do this. Let's do ega gr without the -i. We'll do star.c, we'll pipe that to more. And we should get a fair amount. And we have here IDCA, IDVW. Ooh, an IDVW on the next screen here we have gr mode equals ega gr. So let's take a look at idvw.c and see if we can find that. Search find, and again, we found that gr mode from before, so I'm going to go for that. And we have the compiler directives, and we have the variable in C, both here, CGA, screen width 80, and then we have this function set screen mode, so let's take a look at that. Okay, so let's scroll down. Okay, so for our text mode, we've got AX to 3, for CGA 4, and for EGA 0D, which, as you recall from the VIS documentation, is one of the supported modes. So we're going to have to hope the game doesn't get all fancy with custom palettes, because VIS only supports 4 static EGA palettes, and if you try and update a single palette slot, it will match the entire palette. If the slot you're updating matches the code you're updating, it'll just update the entire palette. But we'll take our chances with that. So here we go. We know that it's 0D. We're fine. So the last thing we have to take a look at is the controls. And this is kind of the most complicated part of the whole thing, because I was pretty sure this was going to hook int 9, and it turns out I was right. So back to KD main we go. So we're going to search find, and it's going to take us to US text, and this takes us back to our US text screen. So now we've dealt with this. We're going to comment this out. We've got our VW startup for our video modes. The next was in startup, so let's look there. idin.c. And this is where the fun's going to be. Okay, what we already have is I page down 1, our very first tell. Key int 9, so let's go look for that. And there we are. Right at start keyboard, it takes us right down to a start keyboard function. And what does it do? It hijacks int 9. So of course that's going to have to go. So the biggest thing we're going to have to deal with here is the control. And of course, I want to use this. I want to use the VIS hand control. I don't want to use a keyboard. I'm not going to rewrite the game to use a keyboard on a platform that a keyboard was optional. I want the hand control, friends. So let's go take a look now at the code that I changed. We'll see what changes I made. I'll go through some of the highlights. What I did to get the text screen out, pretty simple. What I did to get the controller to work, less simple. And whether or not I touched the interrupt 2C thing for the system time. So let's go now take a look at my code. So I'm going to go over here, and we're going to look at KD main first. And one thing I like to do is put my name in comments wherever I modify anything so that I can search for TJB. Search for TJB Chris. And here we go. US text screen, VIS says, no dice. And of course down here, like I said, still more no-go from VIS because there's no text screen. But I left the remainder of these intact, so we know we don't care about RF, but we're going to have to look at VW, and we're going to have to look at IN, and we know that. Okay? So we have a few setups and startups here. So let's go take a look at VW startup, which will be, of course, in ID vw.c, search find TJB. Okay, here we go. And you'll recognize this code from the unmolested code from before. This time, I actually turned off video card detection, and that's because I know the video card is there, but I also know that the video card does not respond to all of the same calls and modes and things that a standard PC EGA card would. Therefore, I didn't want video detection to throw it off. I figured I'd force the issue and see if it would actually run on the VIS. So back to KD main. And our next one is, of course, in startup, which is going to be in IDIN. As you can see, once you get used to the system of file naming in this, it all becomes fairly clear. And in IDIN.c, I'm going to look for that startup routine. Search, find, that's IN start. Okay, there we go, IN startup. Okay, did we do anything here? Now, there is joystick and mouse support in this game, which I just kind of glossed over, and I left it alone. I didn't touch it. And I didn't use the joystick or the mouse because those were very convoluted, even more so than the keyboard. So I figured I didn't really want to deal with trying to unravel that when the keyboard looked like it was going to be easier. And I didn't go through the keyboard on the untouched code side because I can explain how it works without having to walk through it. So I see here we have INL start keyboard, which, as we know, was the function that resets the interrupt for int9, the vector for int9. So that's where we're going to want to go look. So let's actually go and start there. Start KVD. So in taking a look at start keyboard, now I think is the time when we actually have to talk about how the keyboard in this game works. This game is a little interesting, and actually some of the games that I've come across are fairly interesting in that they set, for example, this game sets an int9 to its own custom routine, but the routine only maps to a in-memory version of the key map that's stored within the game, and then the game continuously polls said key map to figure out which keys are down. All I have to do then, when I got looking through it, is translate the VIS controller buttons to the individual keyboard keys that I want to map. And that's the tact I took. I thought, I don't want to rewrite the entire game. It's dependent on the keyboard for its keyboard routines when I can just take the keyboard input part and replace it. And part of the thing that came to mind is, if you remember back to the VIS BIOS documentation, there is specific support for setting functions that the VIS can call every time you press or release a button on the hand control. So kind of like hijacking int9, but not. The VIS automatically calls this routine anytime you push a button, and all it does is checks an address that you set via an int15 call, which you're now looking at on your screen. That's the Word doc that's there. Highlighted on the screen for you now is the set and get routines for setting up the switch handler, and I can set that routine. So what I did was I decided that I would, back to start keyboard, what I decided I would do is I would go out and I would get a pointer to the INL key service routine. That is the existing name of the function that the program used for its keyboard handling routine. And as you're about to see, I completely rewrote that one too. And then what I did was, of course, just like in the original game, I cleared the original keys, set them down. And then what I do is I get the segment and offset of the controller handler here, so I've got my controller handler. And then we get into a little bit of inline assembly here, and I say instead of hijacking the keyboard ISR, we'll configure the hand controller handler here. So what I do is read the address of the existing hand controller, and we do this with inline assembly. So I call AL01, AH71, which you can do with a single move over into AX. We set BH2, which is the code for get the hand control. And then we call int15H, which is where VIS has its custom interrupt handlers. And then, this is one of the great things about inline assembler and C programs like this, is I can take and move the contents of the DX register, where the segment, and the SI register, where the offset comes back, and I can stick them into C variables, assuming they're in the same data segment, and problem solved. So now I've just taken the existing handler address and stored it so that if I were to exit the game, I could restore the handler on the way out the door. Then I set my new address, and as if you recall here, fseg and foff are the segment and offset of the pointer here, which points to the INL key service routine, which we'll look at. Okay, so back to this. Now this time, same thing, 7101 for hand control services, BH equals 3. We're going to set the handler now, and then we're going to move the contents of the segment into DX, the contents of the offset into SI, just like the documentation says, as you can now see on your screen. Then we call int15, and then once we're done, we restore all of our registers and flags, and we're done. So instead of doing the original code that you saw in the previous unchanged IDIN.c, where it simply took setVect, getVect, and setVect, and replaced int9 with INL key service routine, I have told the VIS, oh, nope, INL key service is now your control handler, so every time you get a switch change, just call this address. So now let's take a look at the INL key service routine. You'll recall that is the function within the program here that we actually set the VIS control handler 2, so let's go search for that, INL. So anytime a key up or key down happens on this here hand controller, you'll see that this particular function will get called. Let's see here. So I care about the following keys. I care about pause, escape, up, down, left, right, left control, and left alt, so fire and jump, F1. So then I can say, well, these are each of my keys, my scan codes. Pause is E1, escape is 1, up, left, right, down, blah, blah, blah. Switch it up like Nintendo, right, friends? But it's fairly simple, and again, right back to inline assembler, because why not? When you've learned something new, friends, you tend to stick with it. So I'm going to preserve my existing registers, flags, disable interrupts, which should happen on an interrupt function, but just in case. And then what we're going to do, and this is very simple, I want controller 1, so I'm going to move the contents of the CX register, which is controller 1, again DX is 2, and I'm going to take that into a variable I called control 1. And like I mentioned, VIS returns all of the buttons in a single call. So you don't have to scan it over and over again. You're going to get the state of all the buttons every time one button is pressed or released. It's actually pretty efficient, friends. And then what I do here is I play a little bit shift fun. I do a for loop through the 10 bits that I care about. Oh, but TJP Chris, you're saying to yourself, the VIS controller state comes back as a word, 16 bits. Why do you only go through 10 when there are 16 bits in a word? Well, that's because there are only 10, count them 10, buttons on the VIS controller. And there are only 10 bits associated with those buttons. See the documentation now up on your screen. See that red box highlighting them? There. So why waste the time rolling through bits that don't matter, aka bits 10 through 15, when you don't need to? So we're just going to go through the ones that we know are implemented. That's 0 through 10. Ostensibly, the remaining bits would have been used on future versions of these controllers had they ever existed. I go through and I do a little bit of looking to make sure that the value hasn't changed. This first bit thing here is for me to figure out the last scan, last ASCII codes for this so that I can figure out which value changed first. Now, this is flawed in that it always starts from the least significant bit. So if two things change at once, it's going to find the lowest bit first. So it's not perfect, but you know what? Whatever. That doesn't matter. But then I take, for each bit that I walk through, the array value, and we'll look at VIS codes in a minute here. I set the keyboard value, and the VIS codes is actually a lookup that equates which VIS bit position equates to what keyboard scan code, and I'll show you that. And then I just simply do a shift on it based on X. So shift left 1, 2, 3, 4, 5, 6, 7 times. And there we go. I'm sorry, shift right. I'm shifting right here, not left. And then I, of course, increment my loop. So let's find VIS codes, and then I'll come back to this. Find VIS codes, and here we are. I just set these at the start of the program. They're constant. And these are the keyboard scan codes for each of the buttons that I mentioned, you know, pause, escape, etc. So there's our escape. So that is 1, 2, 3, 4, 5 in. So 1, 2, 3, 4, 5. Button 4, which is button 4, that's the what would be the select key on a Super NES controller. That is the escape key. And then we have, you know, left, up, and right. And I use the hex codes. So back to INL key service. Now, the game has, first thing I do here, of course, I just mentioned my first bit here. So the key code becomes the lookup of the first bit that I found to be different. Again, first bit from a sequential walkthrough of the bits. So I shift writing. And then we go through, are we special button code? If not, we do, the rest of this is the game's logic. And then what I do here is I reset my various counters because, again, you have to remember this is an interrupt function. It's going to live in memory. These placeholders aren't going to change. So if VIS calls it again, I need to make sure that the values are in the same position when the function comes back again the next time I press or release a key. Then, of course, we pop our flags. I'm going to pop some flags. Only got 20 registers in my pocket. We'll pop those. 20. And because this is not an actual interrupt function, VIS is calling us from its own interrupt function. I don't need to do the extra step to end the interrupt function that was in the original INL key service. So this is the original code. I just left it for some dumb reason. So that bit of fire hose, that's pretty much how this works. Easy, right? Right. Actually, this really wasn't that hard. So, okay, enough looking at code. What does Commander Keen and Keen Dreams actually look like on the VIS? I think you'd like to see that. I know I would. Now, because the VIS has the serial loader card in it, I've got to start RF server and point it to a directory, even if I'm not going to load files off the PC. And in this case, I'm not. I've got a Commander Keen disk. We're just going to use it. But I'm going to set RF server, and I'm going to point it to temp. And there's nothing. There's nothing there. This is just files and programs I use to set up the computer. So I just pointed it here. I also have the original source to Keen in here and some other things. This is just all the setup programs for all the stuff on this PC. So let's flip over to the VIS. Okay, over at the VIS, I've got my very official, and this is actually official because I made it, Commander Keen and Keen Dreams. This is a direct boot disk. It will boot straight into the application. And because, if you remember my discussion from licensing in the first video, I'm a Class A guy, this is a Class A title. Fully blessed by the current gods of VIS. I don't know who they are. It ain't me, friends. Okay, so we're going to boot up, and I'm going to hit Control-Alt-Del here so that it sees RF server. And apparently oh, you know what? Remember when I used the DT100 to use DOSMON to figure out what was going on with Commander Keen? I never plugged the VIS back in. Hold, please. Okay, now that we finally got the cable plugged back in, tragedy averted, it's time for a whiskey break. This break is brought to you by whiskey. All right, just a nice little sip of whiskey. All right, so let's give this thing the old three-finger salute. And we should get, there we go, VIS boot. And again, Class A title, because I'm a Class A guy, friends. And now what you'll notice when this thing starts up, you're going to be lacking a text screen. It should go straight to the graphics screen. And now, one thing I have a tendency to do when I'm playing games, any of these games with a hand control, is I tend to go low in my lap with them and just kind of relax it on my legs. And I can't do that with this because it'll be below the table, and the IR blasters on the remote won't actually be able to reach the VIS. So I just push a button here. And now you can see here, it responds. I've got my arrows to move the cursor around. Got to aim it at the VIS, you dummy. And in fact, I've even customized the help for the VIS. So here I note that it's the VIS game. This is a port by yours truly. Actually, I called it this thing resembling a port, which is pretty much what it is. It's scaffolding, duct tape, baling twine, you know. There's no keyboard support. There's technically no joystick or mouse support. The joystick code's there, but there's no hardware for it. And the mouse, I guess you could try vismouse.com on your CD, and maybe it would work. But again, it's the VIS. It uses hand controls. Okay. There's no save or load functionality yet. We'll talk about that in the next video a little bit, why that's a thing. And maybe long-term there'll be something we can do about that. There's no high score screen. In fact, I did fix that. It just picks a random name for you. There's a control panel. And then, of course, I did do one too many. Said the buttons are a little finicky. There we go. I also put VIS-specific controls in this. So you can see what you need to do. Controller to solo. There's a switch right here. How you move Keen, left, right, up, down. The 2 button, so 1, 2, probably can't see that. 1, 2, and then I've got, what's that? A on the top and B on the bottom. So the 2 button jumps, the 1 button throws. I tried to make it as easy ergonomically as possible. You can jump down with the 2 button, you can duck, and function keys. A gets help, that's the top yellow button. B configures controls, not recommended, which actually I think I changed that. 3, which would be in the place of the start button on a Super NES controller, pauses the game. And 4, select button on a Super NES controller, exits the current game. So if I push 4, and let's go actually play Commander Keen. So I'm going to play the easy game. I suck at this game, so we're just going to play the easy one. And here we go. I can move around, up, down, left, right. And if I push the 2 button on here, it'll take me in there, and you'll hear the ad-lib sound effects. There's no music, but there is ad-lib sound. And I have the volume down so the VIS sound effects don't drown me out. Here I can jump, pick up these things, and I'm actually pretty happy. Can I get you? Yeah. Oh, wait, give me my ball back. There we go. I'm really happy with how responsive the controls are on this. Honestly, this was like this. I've refined them a little bit. It still needs some refinement, but this was like this pretty much out of the box. I was really surprised, but I guess given how the keyboard worked and how int9 was really just updating an in-memory keyboard table. I say this as I'm sucking, but that's because I'm talking. And then the game is polling the in-memory keyboard table. I guess as long as I wasn't too inefficient with getting those values all set up, it would make sense that it would actually work fairly well. And honestly, it's pretty responsive. I've had emulators on modern consoles for older games be worse than this. But I'm really happy with how this turned out. And again, this is scaffolding and duct tape, folks. I've never done, before May, June, when I started doing this, I'd never done any of this. And this port was working, geez, I want to say sometime in July. I had it for Tandy Assembly, and it was working before that. It's not perfect. It's got some eccentricities, mainly with the escape button, and it seems to see it multiple times, but I could probably fix it. And again, there's no save. Oh, I almost bit the bullet on that one. I can never get that lollipop. But I'm overall really happy with this, especially as a first attempt at a port. I've never ported anything in my life. I've never done x86 assembler before. I'm pretty happy with it. And honestly, it's a fun game. I actually got this idea from a member of the community who said on Discord, you should port Commander Keen. And this is the one that had source code. But I think if this exercise demonstrates one thing, friends, it's that when you're porting games to this, you need the source code. Without the source, you can't just patch out. Oh, you can't just. Anytime says, why can't you just? I grimace, but you can't just patch out like an int9 hook. Especially for something like VIS, where you don't just hook an interrupt. You actually have to, you set a switch change handler through an interrupt, but you don't just hijack the interrupt like you did with a keyboard. And even then, the VIS documentation is clear even with a keyboard that's not going to work. So overall, I'm pretty happy with the game. So let's wrap up. So like I mentioned, the Commander Keen source code is available open source, but of course the assets and the intellectual property are not. So eventually this will show up on my GitHub, and I'll put instructions on there for how you can make a disk. I'll have executables and source code, and you'll be able to go out and make a disk assuming you have the Commander Keen in Keen Dreams assets. They're out there. I had a copy here, so you should be able to find them, but I can't distribute them legally. So there you have it, folks, my first amateur port for the VIS, Commander Keen in Keen Dreams. In this video, I wanted to share not only the technical aspects of getting Commander Keen to work, but kind of how I got here with the VIS. I wanted to share the Coco emulation because that was a step up to this. I wouldn't have done this if I hadn't done that. And some of the exploratory things I did with QuickBasic, I wanted to share all of that because I literally went through that progression, even though I kind of recreated it here for you. Watching me learn is boring, and I really don't feel like setting up a camera for that, so I figured I'll just recap parts. But I figure at least I can kind of show you the high-level differences, and I hope I explained fairly well the differences between the two versions of the program and how the VIS works and how I could kind of intermingle the two and make an actual runnable game. So I'm pretty happy with the result. I hope you are. And what's next? Well, next we're going to talk about the Save It card. We're going to talk about how data is stored on the Save It card. We're going to take a look at the programming libraries, write some sample data to a Save It card with an application that runs on the VIS. And then we're going to take out the Unicorn developer card with the Save It interface, pop it into my 4833, and then I think I'm going to try and write an executable file to that card. As you recall from my previous video, I have a Tandy card which has a program called VIS modes on it, which documents the VIS video modes, lets you do a bunch of tests. That is the only bootable Save It card I think any of us has ever seen. Well, I hope to make another one, my friends. We're going to use utilities, and that Unicorn developer card on this 4833, we're going to take an executable I've written, and we're going to put it on the VIS without a CD in the drive. What do you think? Fun? I think that sounds like fun. So until next time, I'm TJB Chris. Thank you so much for watching, and I'll see you next time. Cheers.